All right, section 10.3. We're going to continue where we left off last time. We had done the calculus components of this section as they related to derivatives and slopes and things like that. We're actually going to do the antiderivative components of that this time. And so we're going to start with theorem 10.8, which references arc length. So arc length specifically, you've done arc length in, I can't remember if it was, I think it's in Calc 2, towards the beginning of Calc 2. But we're going to look at arc length in this one from a perspective of parametric form. So if a smooth curve C is given by these equations, x and y, and C does not intersect itself, we wrote this one down last time, then the arc length of C over the interval is the integral from a to b of the derivative of x squared plus the derivative of y squared. We take the square root and then we integrate, okay? So taking a look at our first problem of this, finding arc length, we're going to have to find derivatives in order to put them into this form that we were just given, right? So we need the derivative of sine t cosine t. So what is the derivative of sine t cosine t?
Negative sine squared t plus cosine squared t.
Yeah. So what did you use to get to that point?
Product rule.
The product
I
rule.
was like, there's a name.
There's a name for it. It is. It's so the product rule says we would have the first times the derivative of the second plus the second times the derivative of the first. And Adeline had already jumped to the consolidation of that, which is negative sine squared t plus cosine squared t. Okay, ready to get to that? Okay, we're going to do the same thing for y now. We need the derivative. So what is the derivative of sine squared of t?
2 sine t cosine t.
Mm-hmm. And what property are we using for that one?
Chain rule.
That one's a chain rule one. Excellent. All right, so to find arc length, we're going to do the integral. It tells us our interval for t. It goes from 0 to pi over 2. As we get further along, there's going to be some cases where we're going to actually have to figure out what those interval limits are with some other constraints involved, just so you know. But this one, of course, we are not. We've been given it. And we need each of these squared. So I have negative sine squared t plus cosine squared t squared plus 2 sine t cosine t squared, and then dt. Okay, so we need to simplify. We need to do some squaring. Remember, we need to multiply a binomial times itself. Don't just square each piece like my Calc 1 students continue to do with different things, right? It happens. It happens sometimes even otherwise, but we want to be careful. So we're going to get the same square root we had before. We've got now sine to the fourth of t. And then the inside term is negative 2 sine t, sine squared t, cosine squared t. We have the last term squared, so it's cosine to the fourth t. And then we need the square of the 2 sine t cosine t, which is 4, and then sine squared t cosine squared t. So taking a look at that, it looks kind of like a mess, but things actually clean up and simplify really nicely. That will not always happen, but it often is the case. And so we want to sort of expect that we're going to be able to do something and see if we run into problems. These two can be combined. And when they're combined, it looks very similar to the first piece that we had already without that last piece added in. So I have sine to the fourth of t, and then I have positive 2 sine squared t, cosine squared t, and then I have the cosine to the fourth t. So this factors, and you might be looking at it and going, that's really ugly. How do I know for sure that it factors? Or if I didn't know for sure, how would I be able to see it? It actually is almost identical to what we have right here. It's just that the middle sign is different, right? So if you think about sort of going back up from the line that's underlined in pink, we got that from having this piece squared. So it should be the same thing, but what's going to have to change in order for it to be the one we need for this expression? Yeah, the sign part's positive. That's the only difference. Are you good with that? Everybody all right in seeing that okay? Okay, good deal. So we see that happen, not always, right? But there is some frequency with which that will happen. So just sort of be prepared for looking for that kind of a, I don't know, a trick maybe, if you will. So, oops, I meant to do like this. So this is sine squared t plus cosine squared t. And, sorry, I've got too many parentheses. There we go. And then, of course, the whole point is that that will eliminate the square root and the squares because it's right here. Okay, so we're getting close. What I have left now is sine squared t plus cosine squared t, which is 1. That's great news. So you have an integral from 0 to pi halves of 1 dt. I should say 1 dt, which of course is just t, and evaluated at pi halves down to 0, so we get pi halves. So the length of this arc from parametric form is pi over 2. So arc length is one application that we're looking at of antiderivatives for this. Yes, sir.
Whenever we're looking on how to like simplify the big mess of sine and cosine
Yes.
down to the simple one, is it cool if we like write in like a substitution where like sine squared is x,
Sure.
cosine squared is y, just
Absolutely.
to make it easier to look at?
Absolutely fine. Yep, you can definitely do that for ease of clearing it up and stuff. Definitely good. Yep. Okay, there's another application of antiderivatives, and this one's going to be the area of a surface of revolution. Now, this should not be a freak out moment because this is not a solid of revolution. It is a surface of revolution. Solids of revolution is what you did in Calc 2 that had like washer method, the disk method. Y'all know I'm talking about the shells, all that stuff, cylindrical shells, right? And then right after you do all that in Calc 2, you learn about the surface area, and you find out the surface area is actually really easy to calculate, even though the solids of revolution were actually difficult to calculate volume for. So here we're finding area, the area of a surface of revolution. So we have a smooth curve. It's given by these equations. They don't cross themselves again. So then the area of the surface of revolution is given as follows. And you'll look at it, and they look like they're almost exactly the same equation we just did, right? Almost exactly the same. So what's different between the arc length that we just found and the area we're finding here?
2 pi.
2 pi is part of it,
And we have the function.
and you have the function. Good. So I'm going to highlight those just to draw your attention to it. These two pieces are included when they weren't included before. So jot those down, and we'll talk about what's going on here. G of t, just as a reference, and you might want to just draw it in, it's written above, but this is your equation for y, and the f of t is the equation that you're given for x. Okay? So each of these depend upon which axis we are revolving around. Are we revolving around the x-axis or revolving around the y-axis? So if we're revolving around the x-axis, we use the equation for y, and if we're revolving around the y-axis, we use the equation for x. Why do you suppose 2 pi gets included here when it wasn't before?
Because it's a full revolution.
Yeah, we're looking at like the area of a circle, right? An area of a circle would be 2 pi r squared. You get that 2 pi that's involved that you didn't have before. Okay, so that's where that's coming from. All right, so let's do the example for this one. So we're going to do it both with the x-axis and the y-axis. So x-axis is first. So as with the others, we need the derivatives, like as in when we did arc length, we need the derivative of each of these, but you'll notice these are very nice and clean. All right, so we've already done one that had some of sort of the messy components to it, so we're going to do one that's got some cleanness to it. What's the derivative of x? 1. And what's the derivative of y?
-2.
-2. Okay. Boy, that's nice, isn't it? Yes, it is. So they're not all messy. And we're doing this with respect to the x-axis. So if I'm using the x-axis, I want to make sure that I'm using the right equation, right? So I've got my surface area. It's 2 pi. The integral is going from 0 to 2 because they gave me those as my t values, and I need to use the equation for y. So the equation for y is 4 minus 2t. And then I have the square root of each of those derivatives that are squared. So the derivative of x is 1, so it's 1 squared. The derivative of y is negative 2, so it's negative 2 squared. Now, the square root part is going to be the same in both of these that we find. And what's the square root going to simplify? The square root component going to simplify to? Yeah, the radical 5, right? So I'm going to get a square root of 5 out of that. If you'd like, and I kind of would like, I'm going to put my square root of 5 in the front because it's a constant multiplier and I can pull it out. And then I can leave the parts that have variables in them underneath still. So I have the 4 minus 2t that we will integrate. If you don't want to pull the square root of 5 out, that's fine. It's on my notes, I actually left it in. But so this would be 2 square root of 5 pi. And then the antiderivative of 4 is 4t. And then negative 2t. Negative t squared. Excellent. And we're evaluating from 2 down to 0. Obviously, evaluating that at 0 is 0. So in some sense, we're really only going to be evaluating this at 2. So when I plug in 2 into this, I have 4 times 2. I'll write it out. So that's 8 minus 2 squared is 4. And then I'm going to subtract off the 0 at the end. So all in all, that gives me a 4. So this is 4 times my 2 would be my 8 square root of 5 pi. The delay is always funny, huh? Yeah. All right. Is that okay? Now, the other one we do is going to be only slightly different. What's going to change?
The function in front.
Yeah, the function in front. That's the only thing that's going to change. And in fact, it's a simpler function. So we have s equals 2 pi integral from 0 to 2. The function now that we have is just t. And then because I've already done it before, I know this is square root of 5, so I'll just put in square root of 5. So again, if you would like to pull the square root of 5 to the front, you can. If you don't care, then just don't. The t then becomes what? What's the antiderivative of t?
1/2 t squared.
1/2 t squared, or you can write t squared over 2. We're evaluating from 2 down to 0. So again, evaluating at 0 gives me nothing, but this is 1/2 times 4, and then minus my 0. So what will this give me in the end on this problem? 4 square root of 5 pi, or 4 pi square root of 5, yep.
That's a lot.
Okay, so this section is really like, there's a ton on there. I know, like Alex is looking going, there's a lot of written work problems. But they're all basic calculus stuff, right? Derivatives, antiderivatives, they tend to go very quickly. I know we took a lot of time to do this whole section, but that's just because there's a bunch of different types of topics within it, not because the topics or the questions themselves are extremely difficult to do.